Okay, so we're given a block, and this block is attached to a spring which is hung on some sort of surface. We can consider it a ceiling. And a special constraint on this problem is that as of right now, the effects of gravity are null, i.e., we can assume there is no gravity as of right now. So what that means is this spring right here is hanging in equilibrium, and it's not being affected by gravity. So some in terms of like actual numbers, we're given that the mass of the object is this should be 200. This is sorry, 2 kilograms, not grams, and the um, force constant of the spring is 500 newtons per meter. That should be purple, and that's basically all we're given. And so the problem asks for us to find, well, if we were to hypothetically turn gravity on, this block is going to fall. And at some point in time, the block is going to stop falling and start going back up, and it's going to enter simple harmonic motion. And we're asked to find what the amplitude of that motion is. So, well, basically, what we're given is this block right here. This block is going to fall a certain way, and it'll fall, and it'll start oscillating up and down about its new equilibrium, and we want to know what the amplitude of this oscillation is. And so I believe that this is a very good culmination problem for all of the, or generally most of basic physics mechanics. It contains springs, it contains simple harmonic motion, basic kinematic functions, and basic Newton equations. So the Newton's first law. So a lot of different things are used in this. So take a bit and pause this problem and try and figure it out by yourself. And we're going to start, well, basically right now. So the first thing that we want to do this problem is we want to kind of figure out how far is this block going to fall before the force of the spring counteracts the force of gravity. So this block is going to fall a certain way, at which point the spring is going to exert some force um, here, and this gravity is going to exert, well, the same force. It's constant, and we want to know when these two will be equal, specifically how far will the block have fallen. And the way we do that is we set up a basic equation. So we're going to just simply set up, we've got the force, and so we're going to use our first formula, which is F is equal to kx. Rather, negative kx, for our purposes, we can just set it to equal kx because absolute values. So F is equal to kx, but F is also equal to mg, and this is in terms of absolute values, which is why we can do this. So mg is equal to kx, and we just simply plug in values. We're given m, which is 2 times g, which is 10, is equal to kx, and kx, well, that's actually just 500x, so this gives us 20 over 500 is equal to x, and x is in terms of meters. Convert this to centimeters by multiplying by 100 on the top and bottom. So we'll first say x is equal to, we'll cancel this and this, 1 over 25, 0.04 meters, which is 4 centimeters. So this block is going to fall 4 centimeters. And then at that point, gravity is the force of the spring is going to counteract gravity. Now, what we're going to do is talk things through in terms of some relations specifically related to how are we going to figure out now what the amplitude is. Well, first off, it's natural to ask, is there even going to be an amplitude? And the answer is to that question, yes. So as it's falling, it's going to fall. And it's got this positive, or I guess you could say whatever, let's define positive to be pointing downwards. So it's got this positive force acting on all the way till that point, and then it's zero. Which means it's going to have positive acceleration the entire way as it's falling to this 4 centimeters. For these 4 centimeters, it's got positive force. what that means is it's got positive acceleration, so its velocity has to be positive considering its velocity started out at 0. Since its velocity is positive, we know there's going to be an acceleration, and there's going to be amplitude, which is not 0. So how do we find this velocity per se? Well, first let me delete all of this. And so we know, and actually I'll move it off the screen so you guys can't see it, but I can pull it back whenever I need. And that didn't work. So what we're going to do now is we're going to take a look, okay, what's the force throughout this entire period of time? So what we want to do is we want to use one of the kinematic equations we know, which basically relates acceleration times and it basically has acceleration, distance, velocity 1, velocity 2. And for that, we'll need to calculate the average acceleration of a distance. And that can pretty easily be done, the average acceleration over distance. But first, what we want to do is find out what is this kinematic equation that we're looking for. So we want to find out what is the kinematic equation, which has the variables the v1, v0, because v0 is initial, v1, the acceleration and distance. And once we have that, we can kind of solve for this equation. So pause and take a moment and think what kinematic equation works for this. Well, the one that we're looking for in particular is going to be, well, the fourth kinematic equation, which basically says Vf, or V1, or however you want to put it, squared, is equal to V0 squared plus 2a delta x. And this is why I said we need to average the acceleration. And if the acceleration is changing, well, yeah, like we said, if we just average the acceleration basically just goes from 10 meters per second squared to 0 meters per second squared. So that's an average acceleration of 5 meters per second squared applied constant. So that should hopefully make a bit of sense. The average acceleration on this object is 5 meters per second squared. And this is, so v0 squared is just 0, so 0 plus 2 times, this is 5 meters per second squared, times delta x. What is delta x? Delta x is 4 centimeters. They want this in meters, always meters, meters, meters. Meters, well, this is 0.04. So this is 0.2, 0.4. So Vf squared is equal to 0.4 meters per second squared. A meter squared per second squared. And so we square root this, and we get Vf. Vf is equal to the square root of square root of 0.4, which is just 2 times the square root of 1 over 10, which is 2 times the square root of 10, which basically is this, which is square root of 10 over 5. So that's the final velocity. Now that we have this final velocity, we can set up an equation with respect to potential and kinetic energies. And so for springs specifically, the potential energy at any point u is going to equal 1/2 kx squared. And the kinetic energy, well, we know it's 1/2 mv squared. So the kinetic energy and the potential energy, they have the same sign. When the block is at its equilibrium, we know that the kinetic energy is going to be maxed because of spring laws. So Ke, so the kinetic energy, is going to equal to 1/2 mv squared, which is going to equal 1/2 times mass 2 times v squared. That's the square root of 10 over 5. That's going to be 100 over 25. Sorry, 10 over 25, which is 10 over 25. And this is going to just equal, well, these cancel, and these cancel, that's 2/5, is equal to 1/2 times 500 times x squared. That's huge, but this is going to give us 2 over 5 times 250 is equal to x squared. Now, isn't that big? And what this is this is equal to 1 over, and actually, let me simplify things here a bit first. This is equal to 1 over, well, what is that? That's 2, so 125. 125 times 5 is 625, is equal to x squared. And so this implies that x here, and x is the maximum amplitude, is equal to 1 over 25 meters, or 4 centimeters. So yeah, 4 centimeters. That's the amplitude if this block is dropped from that height. This block is dropped such that that's at equilibrium. So yeah, that's basically it for this video. I really hope you guys did enjoy and learn something in this video, and I hope this was a challenging and fun problem for you guys. If you did enjoy, please don't forget to like and subscribe, and I'll catch you all in another video. Goodbye.